I would like to thank Fomidin for organizing this wonderful workshop, which I learned a lot. Today I'm going to talk about some joint work with, that I've done in the past few years with my collaborators Chen-Jun Lang, Jin-An. They're my students. And Yue at Lehigh, and Haibo Li now is at Melbourne. And Jin Chao Feng is at Great Bay University. And Sheng Wang is at Johns Hopkins. And Ivana O is at Delaware. And Neil Chatham. He has been moving. I forgot where he is now. And so the support is from Johns Hopkins and National Science Foundation. So let's return to this learning kernel operators. In a learning setting, what we are trying to do, in my view, is we are trying to approximate some function. When the function have a variable that is very high dimensional, like infinite dimensional, and the major difficulty, now we are trying to learn some operator or in some more complicated function. And the point here is we want to find some low-dimensional structure so that we can learn well. And one way to get a low-dimensional structure is that we have a long local kernel that can represent the long local interaction across different scales. So that's where these learning kernel operators come from. Okay. So the talk will be in 4 parts. The first part is about making the problem precise in what I mean learning kernels here. And the second part, I will see that it will become something very simple. It will be regression, and we need regularization. And from there, we'll see some trouble there. And then we move on to the third part about, we try to understand the problem we're studying, what's identifiability, and I will introduce a data adaptive RKHS, which is very important. And in the fourth part, if we have time, I will briefly mention some iterative method. Okay. So the problem we want to study is as follows. We are learning the kernel operators as follows. This kernel is a convolution operator, is a convolution kernel in this operator R phi u. This R phi u is defined as follows. This kernel phi is here, is a convolution type, and this operator depends on u, can be linear, non-linearly, and this gu is a function of u with output x and y. And when in this study, in the talk, I'm focused on this phi being radial, but in general, it can be general kernels. Okay, and this u can be either a high-dimensional vector space or a function space, Banach space. Okay, and the input is u, the output is f. With noisy or numerical error, we get to here. So that's the problem we want. We are given data, input and output pairs. We want to estimate this kernel phi. And in the talk later, I will focus mostly in the case that u and f are functions. And we observe u and f on some mesh. They're like from PDE. Okay. The motivation example for me are the following 2. And the first one is interacting particle systems, which my colleague Mauro Maggiani introduced me to this business. So here we have many particles interacting with each other at ED, introduced yesterday. And these XTI are the position or opinion of the particle agents in the network. And they interact through this interaction potential. And we assume that this interaction potential is radial and its gradient is this one. Its derivative is phi. That's what we want to estimate. And it's a dynamic system. It's a very high-dimensional dynamic system. And given this trajectory of the particles, we want to estimate the interaction potential phi. Okay, that's this finite dimensional setting. When the n goes infinity, we have infinite particles, and we are going to have this mean field equation by the propagation of chaos. And this mean field equation is a parabolic equation, which is the Fock-Planck equation of the McCain-Vlasov SDE. The key point here is this aggregation operator R phi u will involve a convolution here, because the sum here actually becomes convolution. Okay. So in this setting, we are given the data is an observation of the u, a trajectory of u, like this one. This is in time, this is 1D, and then that's the observation we have. We want to estimate the interaction kernel phi here. Okay. And that's one example. Another example is non-local PDE that I learned from Yu. And we have the homogenized model for metamateria. We want to study the wave propagation. We want to build a non-local model where this phi is the convolution kernel, and the u depends on different locations. And this wave propagation, we have the second order derivative here in time. So in these cases, we are given data, these u and f k pairs. We want to learn the kernel phi. Okay. So in this case, we can see here, quickly we will get 2 types of problems. The first type is a statistical learning problem. So if you have random pairs of input-output, we want to study this convergence of the estimator, like is a static learning problem. And if we have finitely many pairs of data, like we have different mesh as mesh defines, we have deconvolution problem, which is the inverse problem. And in this talk, I will focus mostly on inverse problem. Okay. But here, then we want to compare this learning kerning operator and what's the difference between the classical learning. Like we give xi, yi pairs, we want to represent the yi as a function of x, is phi. And another one is the operator learning that we are talk a lot in this workshop. So let's look at the classical setting. Given xi, yi pairs, and now given a observation here, we know that is a small perturbation of the phi xi nearby. Okay. If we have many different observations, what we are doing here is in the learning process, effectively we are doing interpolation. Okay. And if we look at our problem for learning kernels in the operator here, given the UK input and the output, and we can determine no value of the phi at any x because it's non-local dependence, is a convolution, or is a sum. Okay, so that's the underdetermined problem. If we look at our operator learning problem, in this case we are given the input output. We worry about the output itself, RU. There's no kernel to learn. We just learn the operator. In this case, we can see here, given an observation, and then the observation is a local perturbation of the input. If we change this x-axis here to be u instead of x. So in this setting, this operator learning, if we look at the operator itself, we are basically doing this one, except that we are looking at a much higher dimension. Okay. So if we look at these problems in the large sample limit at the inverse problem, and we will see later that this inverse problem of classical learning is well posed. And the operator learning is also well posed. Okay? And the learning kerning operators, we are doing deconvolution, is the ill-posed inverse problem. In this setting, we are going to introduce a data adaptive RKHS to deal with this ill-posedness. And our goal here is we want to get estimators that converges. As Eric mentioned earlier, the pure mathematicians or statisticians prove the convergence result. For us, we are doing computation. We want our algorithm to produce estimators that will converge. We don't prove their theorem, but we want to use their theorem, their convergence rate, to test our algorithms. Okay. So let's get back to the computation. So the regression part, we do here is we're given data, we want to do the regression. And what we will do here is we are putting this loss function, the standard, and then we choose the hypothesis space, giving a set of basis functions, and then we estimate the coefficients. And basically, this quickly become a least square inverse problem. Yes, please.
Can you explain what the G is? Do you need to learn the G as well?
Good point. Great, thanks. That's a good point for me to get back to here. Yeah. So the G here is something given, like in this operator, it will depend on, if we read this thing here, everything in the term of the integration, and we will see this G will depend on the derivative of u and the two u's. Okay, and for this one, it will be uy minus ux. So it's given here. Yeah, given by the operator itself. So that means we assume the form of the operator, and then we do the estimation of the phi. And good point here is, as we are going to just notice over there, is this r phi u can depend non-linearly in u, but it's linear in phi. Okay, that's where our regression will work. So let's fast forward to the regression part. So we know this r phi depends linearly in phi, so we know that we're going to have a quadratic loss function in terms of c. And we quickly get to the A inverse B problem. Okay? And we can choose the basis as we want, RKHS or any basis, B-spline. The point here for long parametric estimation here is we want to get our estimator converges as the data increases. Okay? It's well known that for long parametric regression, the main difficulty is to choose a proper hypothesis space. And if we are using RKHS, that means choose proper band, as Eric mentioned in the first talk. We want to avoid underfitting or overfitting. We can get a balanced fitting to get the optimal rate of convergence. Okay. And okay. So the problem here is, I put that part in red, is because we want to choose this property. That means we are going to run a large set of bases and then narrow down to select the optimal dimension. The problem here is this an, ax equals b, we want this a will be yield conditioned. And this b have noise or numeric error in it. Most time we have both because we are approximate integrals. In this case, the natural thing to do is to do T-curve or ridge regression, depending on your community. So basically we add a regularization term here, quadratic or semi-norm, and then this B star is the semi-norm part. And in ridge or T-curve regularization, the typical selection is this IN, and we put it here, and we do the optimization in both lambda and the C. So to select lambda, usually we do is we select by the L-curve method, which is developed by Hansen for 30 years, and or by generalized cross-validation method, which is widely used with performance guarantee. It's proposed by Waba. Okay, so these two, the green, I mean, this is well known, they are reliable. Now the question is, which norm should we use? Is this IN is a good choice? Clearly we can see first now this, when we select basis, if we use IN here, it does not take into account the basis. We should use the basis matrix. As Ed yesterday mentioned, he wants to normalize this phi. So in some way we want to look at the function space. So what we did is we start from normalizing small L2 in the coefficient space over the function space L2 space. And what we see here is we want the blue line to decay as the red line. The blue line is the estimated error, and the red line is the loss function decay as the x, this mesh refines. So that the x-axis here is the delta x, it became smaller. So we want this one to decay. We see small L2 and capital L2, both when the noise is large, it does not decay anymore, it gets flat. I call this flattening curve. So that's what we want, we don't want to see. And that's the headache part. We tried all the way we can for these two, we couldn't get any convergence. And that's the wall we hit. So as I discussed with Ed yesterday, when I hit a wall, I will take a nap. So and see if it will be solved. So after many naps, I realized one thing here. I read, this is a paper by Andrew Stewart in 2010. It's a review paper on Bayesian inverse problem. And in the paper, he mentioned one sentence here is, avoid discretization until the last possible moment. But here, what we're doing here is, we can also see this similar way is avoid basis selection until the last possible moment. Because when we select hypothesis space, anything we select, we are actually choosing some discretization already. So to study this, then let's return to this operator itself and ask ourselves, which space are we learning this phi? When we view this as L2, like L2 on with the Lebesgue measure. But in many cases, it doesn't work because this phi in the like this Lebesgue process, there is a singular kernel. In L2 will not be integrable. So that's not necessarily a good space. And also, given the data, what can we identify about the kernel phi? So that's where we get back to this function space, study the identifiability, and then introduce the data identifier RKHS. Okay. So the first thing here is we are going to look at where we can actually estimate phi. So given this U as data now, the operator explores this data, the independent variable of phi, only through this GUXY. Okay. So the natural thing to do is we are going to put this X, Y, all the pairs that data give us as an exploration measure. It's like the L2 row in the classical regression. Okay. That's a natural thing, because if we will explore only here, we cannot estimate the phi from other places. So that's the row, that's something basic we should start with. With this one, now we can look at the loss function on this L2 row space. Okay? And at the function level, we are going to look at this quadratic term will give us a self-adjoint operator on the L2 row space. And then the linear part will give us the representation of this data here, give us phi d, and plus constant term. If you take a first derivative of this loss function, set it to be 0, we get this square in the operator sense. Okay, it's LG inverse phi data. And this LG is a self-adjoint operator. Actually, it will be non-negative and compact. If the data is reasonable, it's bounded, basically, and the row is bounded, or L2 integrable in general. And in this setting, now what we're going to have this phi d by representation, it will be two parts. One part is LG phi 2 plus some error. And what we can do is, in this inverse, we put these two together. What we can identify this phi 2 is basically in the perp of the null space of this LG. Because if the LG have zero eigenvalue, that means we are not going to observe anything about phi true in that space, in the null space. We can only observe this, estimate this phi through in this null space, or this space with positive eigenvalues. And we call this function space of identifiability. Okay. And beyond this space H, the problem is EL defined. Okay. If we look beyond this, that means we are going to look at something wrong. We are not going to get anything work. And also inside this H, if H is infinite dimensional, we are doing the inversion of a compact operator, so it's EL post, and we have to regularize in it. Okay. So that's the task now. We want to regularize inside this H and make sure that our search is inside this H. But this H depends on data, because this operator LG depends on data. So how do we get this? And that's where LG again is the RKHS. The LG is a self-adjoint operator. We know that you can find any book on RKHS. Basically, the LG is self-adjoint operator is non-negative. We can define this LG half L2 rule to be RKHS. Okay, that's the RKHS we're going to use. And its closure in L2 rule is this FSOI we just defined. And then with this norm in LG, and we can get the regression. We put this norm here. We do the regression now. What we are going to do in the operator sense, we are going to have estimator is LG plus lambda LG inverse. And if this LG inverse is the pseudo inverse. If we take it out, actually we get to the least squares in the operator sense here in the end. Okay. It's just this simple. It's just the, if we look at the problem in this RKHS, we get an operator sense LG. And the operator sense RKH and these squares. Okay. So in computation, what we do here is we can do almost the same as we have done before, except that we require one more thing. You have your A and B n already, keep them, and add one more thing. You have a basis function phi I phi j. Now give me the basis function of phi I phi j, and then all the rest will be automatic, as has done before. What we have to do here is that we are going to put this RKHS norm inside it, and then all the rest of the L curve, and to get this estimation will be automatic. Okay. The key thing here is to estimate the RKHS norm, we need to generalize the eigenvalue problem. But if you do the also normalization of the basis function first, as Ed did yesterday, and then the BRKHS will be AN inverse. They're in the inverse of your normal matrix. It's something kind of like very strange now. We know AN inverse is the one that gave us trouble. And now we are putting it here to do the inversion and then do the regularization. It's kind of like counterintuitive, right? That's the trouble term, and we are putting in the inside. So our first intuition is that this AN inverse, AN dagger, will kill us. In particular, in our cases, we are going to do this non-parametric estimation. Our the smallest eigenvalue of the AN, it could reach to 10 to the negative 12 if you use the 16 digits accuracy. Okay, and that's what happened in many simulations, and we took many labs, and we got some results in the end. So this is the previous picture I showed earlier. Is for the aggregation operator here. We are given data of U in different, a few pairs of U and F, and we want to estimate the kernel phi because the convolution here, okay. And we tested two types of kernels. One is the sine kernel. We have jump discontinuity here. From here, it jumps to 0. And the second one is the Gaussian kernel is smooth, okay. And we see here the blue line, the dark blue line is always the RKHS. The other red and orange are the small L2 and capital L2. We see roughly here the RKHS do much better than the other two in one simulation. And we also plotted the cyan color is hard to see here is the rho, expiration matter rho. It decays as the get size become larger and larger. And then when the rho is small, we have large estimation error. Okay. And that's one typical simulation. This is the middle part is we have a different mesh size converges. We want to estimate or converge. And we see RKHS converges much better than the other two. Yes. And good, I'm good. So here we want the ideally, the estimation error will converge as the loss function, but in general, we cannot sure about that because the min-max rate may be different depending on the estimator, the operator inversion. But we do see this steady convergence of RKHS regularized estimator. Okay. Of course, in the learning theory, we also know that there's min-max rate of convergence is independent of the scale of the noise. And so we test this convergence for different scale of noise. We call it noise ratio, noise signal ratio. Okay, so the ratio here we compute by the slope of these these lines. And we see here the RKHS have a consistent convergence rate, while the other two can either larger or smaller because the large error can make it oscillate. So in this way, we see that we get robust, consistent convergence rates for this RKHS regularized estimator. So in the end of the lesson here is, if it doesn't kill us, it will make us better. Okay. Okay. So we applied this regularization to an application problem. This is we would call it real data because in this problem we don't have a true model here. And this is the heterogeneous wave propagation in metamaterial. The basic point here is we have this material as different type of material putting together, and then we want to study the wave propagation in it. We want to build a homogenized model to analyze the property of the material. So the data we collect is either from the real experiment or numerical simulation, high resolution numerical simulation. And we want to build a homogenized model in the wave equation in this format. And in this problem, we don't have a ground truth because we don't know which kernel would it be. But ideally, we want to estimate a kernel that is resolution independent so that this homogeneity makes sense. So what we look at this estimator here is for different regularized estimators, different resolution, we see small L2 and capital L2 give us largely oscillating estimators of this kernel phi. But this regularized RKHS give us estimator are largely consistent. What's more is here, if we compute the frequency angle omega square from this transformation of this kernel phi, we want to get something should be positive. But these two give us some negative omega square, which is non-physical. And the RKHS, on the other hand, always give us consistent positive omega square. So in this problem, basically we have tested this case that just simply using this data adapted RKHS, we get an estimator is more or less resolution invariant and is a more or less physical estimator. So basically, the message here is, if we don't put any biased prior from ourselves into it, just use the data adapted RKHS, follow the data, it will give us something physical and meaningful. Okay, and that's the regularization. Then we have another issue here is when we want to send this to 2D, and then the matrix A will be much larger. The dimension will be very large. What we have shown so far in the previous slides, we are using the direct matrix decomposition to compute the RKHS. And when n is large, the n dimension is large, it's hard for us to do it. And the question is, can we do this iteratively? And the data that RKHS actually allows us to search in it. So that's a good thing for us to extend it. So in this process, actually found that this data adaptive RKHS works for any linear problem like this. Even if you don't have function space, you're just solving this Ax equals B. We can also have data adaptive RKHS. So the point here is, we can also transform this equation to a normal equation, and we can compute RKHS. We assign a measure rho to the x variable. So x variable originally is Rn. We don't have any metric on it. We can assign a metric Rn through the exploration through the A matrix here. And then we can also assign a basis matrix, and everything here works. Okay, yes? That's a good one. Here we are going beyond that. This one is for any A x equals B. Even in the learning kernel business, if we don't get to the normal operator, we just look at everything stack a large matrix, we also have this. Okay. And this one actually is more efficient to do in this way. But the point here is this A may have some columns, they may be the same. By doing this row, essentially give us getting off this linearly dependent part and also doing some preconditioning. Okay. So That's the set recovery. We didn't think about this can be work, but it worked very well. And then the main focus here, we are going to do this iteratively because this n is too large for us to write the matrix, the long matrix, do the long matrix factorization. Because the long matrix do the factorization using the SVD decomposition will require O(n) square complexity. But if we use the iterative method we are going to introduce next, it will be 3m is the dimension here times n and times k. K is the early stopping. Okay, it will be like at least one order smaller. When n is 10 to the 5, some scale like that, this is dramatic. Okay. So the iterative method actually is quite a classic setting. We know that we can use the kernel subspace idea to do it. Our main contribution here is we are introducing the RKHS restricted kernel subspace. So we are mapping from RKHS to the R2 space. So we put the RKHS constraint here. Originally, if we use the kernel subspace, which is A transpose B, and then here is A transpose A, without B RKHS. Everything is like kernel of subspace. But here we are using RKHS restricted kernel subspace. And to compute, the idea here is we are going to, instead of searching the whole space, we are doing search the solution in a sequence of increasing subspaces. That's SK is the kernel of subspace. And at a certain level, we are going to stop, do the early stopping to avoid overshooting. And that's where this iterative method works. In the end, if we don't stop it, it will convert to the least square solution with mean norm. So in the process of doing this, we want to use the generalized Galob-Kahan bidiagonalization, which I learned from my collaborator Haibor. And we construct this one in a very efficient way using only matrix vector product. Okay. So with this one, we test this algorithm on two type problems. The first one is the toy problem, is the Fredholm integral equation with polynomially decaying spectrum. It decays very slowly and it's difficult. Okay, yeah, sorry, I need to get back. And what we found here is the iterative method converges very well. It's more stable than the other two. The direct method also works better because in a small problem we can do this more accurately. And we also tried the image deep learning problem, which the matrix dimension will be 10 to the 5 scale. And basically the test that we can do it. Okay, don't have time to do that. Let me summarize what I have here. So in summary, what we have been trying to do here is we are trying to formulate this learning kernels in operator problem. And the key point here is the data may not be able to help us explore all the part of phi. So we have a function space that we can identify phi. And then in this case, we want to use the data adaptive RKHS for learning and for regularization. And in the extreme setting, if the basis is orthonormal, and we are going to do this one for the regularization instead of I, as we usually use. And in the future work that we want to do here is we want to prove the min-max rate of the estimator in the delta X or in the sample size M. And also here in this one, as we have seen here, these are RKHS, we could use this automatic reproducing kernel for kernel regression here. And another thing here is we want to think about this for regularization for general machine learning neural network. We regularize in the function space, not in the parameter space. Okay. The takeaway message I want to emphasize here again is, in the end, if we compare these two, in the classical learning setting and the learning kernel setting is, in the classical setting, if we look at large sample limit, what we are doing is the inversion of an identity operator. But in the learning kernel setting, we are doing the inversion of a compact operator, which may have zeroic values. In this case, the two problems, regularization will have different role. So we need to pay attention to that. Okay, thank you. I will stop here.